So today we will start a very interesting journey. Okay, in fact, we will ask what is known as the fundamental question in learning. I'll post the question in a short while, but let me just recap at least the one of the basic models of classification that we have so far. So suppose we were given a set of points x classified into two groups, good and bad, right? So mathematically your x is a set of points in Rn, and you have a function which assigns either -1 or +1 to it, right? So -1 is for all the bad points and +1 is for all the good points. And suppose these two groups of points were separable by a hyperplane H, right? Then our classifiers, right, be it the perceptron algorithm or the support vector machine, will output a hyperplane H such that the good points are on one side of the hyperplane and the bad points are on the other side of the hyperplane, right? So you can formalize it mathematically as you see here. We are looking, the formalism is not very important for today's discussion. Okay, but what in today's discussion, what we are trying to ask is, I mean, really, why did we do this kind of a thing? We have, okay, now we have a very nice formula which kind of tells which points are good and which points are bad, right? Once you have the hyperplane defined by A and B, you can essentially look at this equation, inner product of A with X. If it is more than B, then it's a good point. If it is less than B, it's a bad point. Great. But we already knew that, right? We already know which are the good points and which are the bad points. Then why, unless you have a fetish for hyperplanes and linear algebra, why should we really try to draw a hyperplane that separates them if your intention is to know which points are good and which points are bad, right? Because in order to find this hyperplane, we anyway needed that information, and we have that information right here, right? We already know which are the good points and which are the bad points, right? So the purpose of this exercise is to convert, to in some sense infer a pattern, or infer from this data you try to generate what can be termed as a knowledge, and hoping that, okay, this hope is a very loaded word here, hoping that this rule, this hyperplane, okay, this hyperplane is what I call the rule that we learn, okay, the rule that we found. Okay, this hyperplane not only separates good and bad points among the points that are given to us, but it also separates good and bad points which we haven't seen, okay, which were not part of X, which were not part of the process by which the training was done, okay, which were not available to the perceptron algorithm or which were not available to the SVM, right? So what is this big hope that we have? We hope that, H will do a good separation. By good I don't mean this good here, okay, let me say, will separate unknown good and bad points too. Okay, by unknown, what do I mean? Those which were not used to find out or to derive this hyperplane H. So that's the big hope that we have, right? I mean, it is a quite a ambitious task, right? But in fact, the whole of machine learning kind of is an area that is built on this hope, right? So let's take let's go back to our first lecture and see pick one example from here, okay? So let us say all these vectors were frequency vectors of emails, okay? So let's say you are working in Google, and Google wants to design a spam filter, okay? So it has to, when a mail arrives, it has to, from the text of the mail, it has to make an inference as to whether it is a genuine mail or a spam mail, a good mail or a bad mail, right? So let's say it represents each email as a frequency vector based on the occurrences of various words, and it hopes to find do a spam filter, right? So the spam filter will finally be under extremely simplistic simplifications, extremely harsh simplifications, let us say the spam filter is this hyperplane, this red line H. So the points which are above that hyperplane are good emails, and those which are below are bad emails. That's what we are hoping to. But how is the spam filter trained, or how is this H found out? It is found out from a collection of mails that maybe human beings who work in Google have already identified as spam or not. Okay, spam or good. In fact, not only human beings who work in Google, even we all kind of do unpaid job for Google. I mean, I don't have a complaint because Google also gives us a lot of unpaid service, but we also keep marking mails as spam, and that whatever mails that someone marks as spam and doesn't mark as spam automatically gives you a training data, right? You get a lot of labeled data among that. But again, the purpose of a spam filter is not to keep on making the human being doing this classification. The goal of a spam filter is to be able to do that automatically, which means it should be able to tell when a future mail comes, okay, a mail that has never been seen before while it kind of designed its H, right? So for a future email that comes into the system, this spam filter is supposed to classify it as good or bad. Based on that, it's a serious decision, right? It will send a mail to a spam folder or not, right? If important, genuine mails go to the spam folder, that's a huge mistake, right? I mean, Google will have to suffer considerable loss if that happens, right? So, yeah, but what is the key point? The key point is not to be able to separate things which we already know are good or bad, but the key point is to separate future things, unknown things also into good and bad. Okay. Then the fundamental question in learning is, when is this possible, right? When can these patterns that we learn from a subset of data, a small collection of data, which is usually called as the training data or the sample data or the training sample, right? When can patterns learned from training data be used to make good guesses about patterns that are outside of data that is outside of the training data? Okay, so a good learning algorithm is one which can do that, right? It is not sufficient to classify correctly what is given to us, because that's anyway we already know that which is good, which is bad. Okay, I think I have kind of said the same thing like 4 or 5 times, but yeah, keep in mind that this is probably the calling it the fundamental question of learning kind of gives you enough emphasis. Okay, right? So let me still kind of rephrase this fundamental question in a few different ways. One way you can ask is like, if you are in the business of running a university, right? You have all these, you train your students with a lot of things, right? You design a curriculum for the student, you kind of design teaching materials and so on. But the question is finally, not whether your students get a high CGPA. Okay, for that actually as teachers it is easy for us, because we just grade everybody so liberally that everybody gets a high CGPA. So but that's not the goal of education, right? The goal of any university is not to increase the average CGPA of students in that university, right? The goal of a student is goal of a university is to nurture students who can succeed in the real life. And okay, I mean, this is kind of taking it too far, but since we are quote unquote talking about learning, right? I couldn't kind of help resist put this example. Okay, but coming to more concrete terms, more mathematical terms, this is the question: will that perfect separator for the test data, that perfect separator with the SCVM or the perceptron algorithm gives you, is it any good on the real data? Okay, it's okay even if it doesn't separate the real data 100% accurately, but does it at least perform reasonably well on the real data? Okay, this this is for people who are who are familiar with terminology of machine learning. You essentially are asking the question: will your separator generalize? So the word generalize is what is used for asking this question, right? So generalize means how good is your algorithm on unknown data, okay, on future data. And a deeper way of asking the same thing is, did it just kind of, memorize the data did your algorithm just memorize the data that was given to you, or did it really gain any knowledge from the data? Okay. So now, like this hyperplane here, I really want to, I'm not ashamed to call it knowledge, right? Why? Because this hyperplane, surely it was derived from the data, it was derived from the good points and bad points that were given to us, but you are still kind of, oh, this is more like an inference that you make from this data, right? Oh, look at these data. What I believe is that all the good points are actually on one side of this hyperplane and the bad points are on the other side. Not only the given good and bad points, it is trying to kind of make a comment about the whole universe, right? It is making a comment about things that it hasn't seen also. That's why we say that, okay, it's a wisdom, it's a knowledge, right? So, okay, so did you really get some knowledge out of the data? That's another way to ask the same question. Okay. Now, what is the answer to all these questions, right? Will our best student really succeed in real life? Now, the answer as happens to be depends, right? It depends on a lot of things. Yeah, but again, there are, when you hear an answer like this, there are multiple ways to feel about it. You can either get disheartened and say that, oh my God, I mean, that's something which you never needed such a build up to answer, right? Anybody could answer this word depends to any question. Okay, so that's correct also. But what I am urging you to do is to kind of, don't get entangled in this question like, okay, let me say it this way. Okay, it depends, yes, but what are the conditions under which you can do this, and what are the conditions under which you cannot do this, right? So the conditions under which you can do it are important, right? Because then that means under those conditions, at least your machine learning algorithm will work. And if you kind of scan your technological landscape around, you will see that machine learning is immensely successful. Google does a fantastic job of classifying mails into spam versus not spam, right? Google does a fantastic job of deciding which advertisement you are likely to click and which you are not. That's the entire revenue model of Google, right? So surely it is working. So we kind of, from the technological success, since we are in 2021, we kind of know that there are a lot of conditions under which this work. Okay, and since this is a foundations course, what we will do is to bring out at least and discuss some of those conditions under which the answer to this question is yes, and prove mathematically why it is why the answer is yes. And in many times we'll also give quantitative bounds. There would be questions that, okay, it will work, but then how much of training data do we need, okay, for this to work? Okay, such questions also we will answer. Okay, so a less dramatic but more useful questions to ask is, so don't just ask can we learn. If you just ask can we learn, then the answer would be just it depends, right? So you have to rather ask when can we learn and how well can we learn when we can learn. Okay, so more concretely, we are looking for the most lenient conditions, the weakest assumptions or the mildest restrictions under which generalization can happen. Okay, so this will take us a long time. Maybe it will take us 4 or 5 lectures before we kind of finish our discussion on this whole area. So we will work with a bit more, restricted conditions under which this generalization can happen, and then slowly start removing some of those restrictions and see how far we can go. Okay, what are the mildest or weakest conditions under which generalizations can happen? And this how well question also we will address along the way. Okay, can we have quantitative bounds, right? For example, there are two kinds of bounds. We can also ask, okay, maybe it won't work perfectly for real data in the real world, but can we say that in the real world it will make an error of at most 1 in 1,000 or 1 in 1,000,000? Can we give a bound, an upper bound on the error probability? And also the other thing I mentioned, can we give a guess on how much of training data will we need to achieve those bounds? Usually these two quantities are tied together. Okay, the more the data we have, a better error bound we will be able to give. Okay, so first, let us analyze a very simple concrete scenario. Okay, so what you see on the left side is the real world, and what you see on the right side is your computer or your office. Okay, so in the real world, let us assume there is a set X of some 10,000 points, okay, huge number of points of vectors in Rn. Okay, and you also have a function X from X to +1 -1, right? So this essentially +1 means good points, -1 means bad points. Okay, so essentially you have 10,000 points and some of them is good, the rest is bad. That is what is there in the real world. But for your algorithm, what the algorithm gets is not this access to the entire real world. What it gets is only a subset S of some, let's say, by the way, all these numbers are kind of arbitrary. I'm just putting them here to have a concrete discussion. Okay, so what you get is a subset S of some 100 points from within this X. Okay, so this S is a subset of X. Okay, remember that this S is a subset of X. Out of these 10,000 points, you get some 100 points. And you have to do your learning, or you have to find a separator for these 100 points, right? So these points are usually called as training samples or training data or sample data or whatever. Okay, and along with these points, you are also given what is the F value for those points. Okay, F value for those points in S. Okay, so, or in other words, we can also say that this is we do not know the entire function F. In fact, forget knowing the function F, we do not even know the entire domain. Okay, so we don't even know the domain, but we know the function F restricted to the subset S, right? This is usually denoted as this F restricted to this subset S. So we know what is the F value of these 100 points that are given to you. Then what do? We find let's stick to this linearly separable thing. So suppose we could find a separating hyperplane A and B, which separates the good points from the bad points, right? So essentially I can also model this as a function G. Okay, since our true world had a function F, we also this hyperplane, I will model it as a function G. What is the function? It is sine of inner product of A comma X minus B. Right, so you remember, if inner product of A comma X is more than B, those were for the good points. So what is inside the sine function will be positive, and then the sine returned will be +1. Okay, so the sine function is a simple function. Sine of X is 1 if X is greater than 0, and -1 if X is less than 0. X is equal to 0 is ambiguous, but that's not an important thing to know now. Okay, so this is just the same hyperplane that we have. I'm just expressing it in terms of a function. Okay, and now what is the $1 million question? The $1 million question is not whether G correctly classifies points in S, but the $1 million question is whether G correctly classifies. So the $1 million question is whether it will generalize to, whether it will classify, whether G, okay, F will surely classify points in X, and the question is whether G classifies the points in X, right? Okay, I have kind of written it as whether G approximates F on X. It's the same question, right? It's equivalent to asking, does G classify X, capital X, well, okay. Now, why do I keep asking well and all? Okay, because I don't want to be too stringent and demand that G should classify every point in X correctly. We are ready to tolerate some relative error, right? It's okay if some, epsilon fraction of the points in X are classified wrongly, right? What we want is that, let's say the number of points, right? So, let's say the error, we'll define what is known as a error of this function g. Okay, so this is the size of those points x in X such that f of x is not equal to g of x. These are the points where your g would make an error, okay, among x divided by size of x. Okay, so there's a kind of fraction of the points in X which is wrongly classified by g. This is called E out of G. Why is it called out of G? So this is usually called as out of sample error, okay, because we are working over all X. There is a counterpart to it which is called as in sample error, E in of G, which is the same thing but for X in S in the sample, right? F of x not equal to g of x, and now here the normalization should actually be by s because that's the maximum, but this for our cases is 0. Why? Because we assumed that we had a separating hyperplane, and once you have a separating hyperplane, perceptron, SVM, whatever will find it, okay. Later we may relax it also. There are things called soft margin classifiers where even within the sample, within the training data, you are allowed to make a few mistakes, in which case En of G won't be 0, but it may be a small number, and still your E out of G, we want it to be again a small number, right? So the question is, can we guarantee a good upper bound for this out of sample error? Okay, so again, whether can we guarantee this, that's an answer to that question will depend on a lot of things, right? So let me first ask a certain probing set of questions to you. So this is the question, right? Is generalization possible? That is, can we have a very small out of sample error under the same scenario that we described above? Okay, so condition 1 or case 1. What if this original data set in the real world, okay, X and this labeling F was far from linearly separable? Okay, then it's an easy guess that you will never be able to do a separation, right? Then it won't generalize. Why? Because the G that you are going to output is based on a hyperplane, right? You are under any, whatever be the sample set you get, whatever be the S you get, you are just finally going to give a hyperplane. And if the original data set is not linearly separable, then no hyperplane that you give will be good for it, right? So that's why I said if the true data, if the real data is far from linearly separable, then you really cannot guarantee any such bound. You may just have been cheated by this samples to believing that, okay, in the samples you got a hyperplane, but in actual data you did not get a hyperplane. Okay, so yeah, so this is the second condition is very connected to it, right? Even if the true data was linearly separable, suppose those 100 points which made up S, right, was chosen by a malicious teacher. Okay. So okay, by the way, why did the word teacher suddenly come in? Okay, maybe I forgot to tell you, this kind of learning paradigm is what is known as a supervised learning. Okay, this is what is known as a supervised, this is one case of a supervised learning scenario, right, where you have a teacher who picks some small collection of data and also gives you the answer. Okay, you also know F evaluated on S. Okay, so that is the job of the supervisor. It will pick you, it will choose the training data, and it will also give you the correct answers, the correct labeling for the training data. Okay, and the next the three questions that we are going to, or the we have here pending, are based on the nature of the supervisor, right? The supervisor can either be bad, neutral, or bad, good, or neutral. Okay, so if the supervisor is bad and if she's a malicious teacher, she can always cheat you by giving you 100 points that are really not representative. Okay, one way that it can really confuse you is by giving all 100 points to be good. Okay, that's one way to really kind of, and then you are almost very likely to make a mistake, right? Or 100 points which are bad. Okay, another kind of way that it may cheat is, so suppose the true data was on this two sides of the plane, right? So this were all the good points here, and you had all the bad points here, right? Now it can really cheat you. The supervisor can kind of cheat you by picking red points this, and then blue points somewhere here, right? So what your SVM or perceptron will end up doing is it will kind of guess this as the separating hyperplane, and then you will, when you essentially evaluate the out of sample error, all these guys here and here will be misclassified and they will contribute to a huge error. Okay, so if the teacher is against you, it's very difficult for you to succeed, right? So what you actually may want to do in real life, what you actually would have needed to do was to learn some Python programming and learn to implement a few machine learning code. But a bad teacher will say that no, I will actually train you on the math behind all those machine learning algorithms. You will get a high score on all these math courses, but out there on the real world you might fail. Okay, so this is also like, so if the teacher is malicious, then again the answer is no, right? You really cannot generalize because the teacher can always cheat you or trick you into a situation which is not good. Okay, so I mean, this, by the way, even though it's not a malicious teacher, this can also happen in some sense unintentionally. Okay, and this is called sampling bias. But by the way, all these things have names, right? Okay, this is called sampling bias. Okay, so for example, right, let us say you want to look at the some attributes of a person and decide if that person will be a good driver or a bad. Okay, or let's stick to the email, good email versus spam email example, right? So suppose this for all these classification, right, Google relied on spam emails being generated from, let us say, spam emails from all the spam examples were from India, and let us say all the good examples were from France. Okay, and then it is clear that what the system will learn may not be to distinguish spam versus non-spam. It may actually distinguish Indian English versus French English. Okay, so this is another way a sampling bias can happen, which may, at least and sometimes, may be unintentional. Okay, but yeah, so much to it. Okay, and this also has a name, right? So if f on x is linearly separable, right, then so the converse, the negation of this, right, is called the I think it's called the realization assumption. Okay, I may be wrong here. The realization assumption. Okay. Yeah, but we'll talk about these things later also. Now don't worry about these names. Okay. Now, the third is S is chosen by a good teacher. Okay, that's a very good scenario. In fact, if your teacher is really good, what should she choose for you? She should actually choose you points on the convex hull. Points which define the convex hull of the good set and the points which define the convex hull of the bad set. Okay, then you can make your learning, you can finish your learning with very few samples if you have a good teacher. So this is, now we are assuming that F is Okay, after this, we already know that if f is far from linearly separable, then the generalization is not at all possible. So for questions 2, 3 and 4, I am assuming that f is linearly separable. So, and when f is linearly separable, the good and bad sets have disjoint convex hulls, and if you take points which define the convex hull and ignore all the interior points are not good things to teach the classifier. The good teacher will only pick the points which define the convex hull, and a perceptron or an SVM will quickly learn from that data. But the problem with this is that this is a very unrealistic assumption, right? Okay, machines have a much worse deal than you students, right? You students, at least, the universities try to create curricula based on a lot of experience, right? As what would be the good things to put into a curricula, what would there are surely subjective things, but usually it's a good teacher model. Whereas in a machine learning context, what is usually assumed, this is too much to ask for. We really cannot hope that we have a good teacher, right? So so a bad teacher will ruin the game. You will never be able to generalize. A good teacher is too much to ask for. So what do we actually work with? We actually work with an indifferent teacher, okay? A teacher who doesn't care, okay? You just pick examples randomly from X, right? So this is what finally we will work. Not exactly uniform from X. What we will assume is that both your S and X are sampled from the same underlying probability distribution. Okay, but in this class we will not go to this model. Okay, this is in fact the key setting of what is known as statistical learning. Okay, so we assume that over Rn we put a probability distribution, and then we pick S, some 100 points from this probability distribution, and we say that if the true data also was picked from the same distribution, then we have a guarantee on the out of sample error bound. Okay, so that is what we will do. But for today's class, we will just assume that the set S is chosen uniformly at random from X. Okay, and last question, does the size of S matter? You will see that it will also matter. Okay, so what are the assumptions that we are going to work with? We are going to work with the following assumptions. Okay, this is the same scenario that was depicted. Okay, you have this X subset of Rn with some 10,000 points, right? Some 10,000 points, and you have this F from X to minus 1, 1. That's the scenario. And but what extra assumptions do we have? Assumption 1, X F is, okay, let me so since it's a toy example, okay, I think it is better that I kind of even further simplify it to R squared. Okay, so to keep the discussion simple, X is a subset of R squared. So things are on the plane. I will be able to draw things like that. Okay, things are on the plane. Okay, and the true data is linearly separable by a line through origin. Okay, this is the simplest case you can think about. Line through origin, right? So the true data is right. So by the way, the points on one side are good. I should have used the colors, but by now I think you. Okay, these are the blue points, and they are indeed separable by this. They are indeed separable by this line. Okay, sorry, it should pass through the origin. Okay, so this is the nature of your true X. Okay, that's one assumption. So this is what I called as the the realization assumption. And then the second assumption that we have is that S is obtained by picking 100 samples from X independently and uniformly at random. Okay, so what do? I have to pick 100 guys from X. So for the first guy, I have 10,000 choices. Each of these 10,000 choices have equal probability. That means 1 in 10,000 probability. I pick my first guy. Okay, and then I replace it. Okay, this is sampling with replacement, because otherwise it is not uniform. You replace it. Second time you again do the same experiment. Third time you again do the same experiment, right? So each of these points that you get, right, your S will be some points S1 all the way up to S100. Each of them can be any of the points in X with equal probability. So that's the samples on which we do the training, right? And now since your whole point cloud X is linearly separable, it follows that X separable would imply that S is separable, right? Think about that if that confuses you. Moreover, our separability is by a line that passes through the origin, right? Now, what do we have to check? We have to check what is the out of SAM. Okay, before that we run either the perceptron algorithm. Let's run the perceptron learning algorithm, PLA, to find a hyperplane. Find a line. Find a line defined by, you don't even need a B here because it's passing through the origin. Line defined by a normal A, right? So A is a vector in R square, right? So what your algorithm will finally find is something which is around like this, right? And in this case, it may not find this plane, but it will actually be finding a plane which is kind of normal to that line. But what is good about A? What is the guarantee on A? We know that A classifies all points of S correctly. That much we know. Okay, so this guarantee we have, right? All the points in S are on one side of the all the good points in S are on one side of the hyperplane, and the bad points are on the other side of the hyperplane. And what is the quantity that we want to analyze? We want to analyze the out of sample error for this function G. Right now, what is the function G? G is nothing but the sign of inner product of A with X. Okay, now this G I can define on, so this G I have actually defined on the entire R squared, right? I can find, using this formula, I can compute G for anything, but I only want to check how good is G on the points in X, right? So that is my out of sample error for G is the number of points X in those 10,000, among those 10,000 points for which your G got it wrong, right? G got it wrong divided by the size of X itself, right? And I want to say that this is less than or equal to some epsilon, which is a very, very small quantity. Okay, this is less than or equal to some epsilon, which is a very, it might be positive, but a very small quantity. Okay. So now since our sampling, we did our assumption 2, right? Our sampling was probabilistic. whatever guarantee that we can give is also going to be only probabilistic, right? Because from among these, when you pick random points, 100 points randomly, it is possible with a very low probability, but it is still possible that the points would be those, the kind of things that your bad teacher, the malicious teacher would have picked, right? It may be the case that all the 100 points were from the good set, in which case your learning will be screwed up, right? Or it might be possible that there is some kind of a bias in the in these samples, right? So this will not work for all S. So there is still a small probability that something can go wrong. Okay, so we are only going to say that, okay, this happens. Your out of sample error is at most epsilon with a very high probability, right? So our future claim is that we'll rewrite it later also. Our claim is that E out of G is less than or equal to epsilon with very high probability. Okay, with high probability, or equivalently the probability that E out of G is less than or equal to this is going to be some greater than some 1 minus delta. Then again delta is assumed to be a very small positive number. Okay, so this is very high. Okay, so this is what we have to guarantee. So we will essentially analyze this probability, right? So our analysis, by the way, this is a toy example, but I think it still has a lot of important things to learn from, right? So we have to calculate this probability of E out of G being, actually we will calculate the probability of the complement of this event. Okay. When would this be more than epsilon? Okay. So I claim that E out of G can be more than epsilon under two types of cases. Okay, I'll just illustrate that. Okay, so suppose this is your origin. I'll need 2 copies of that because there are 2 types of cases. Okay, and let me say that this red line is the correct hyperplane. Okay, this red line is the hyperplane which will separate X. Okay, well, these are supposed to be the same picture. I could have actually copy pasted. I did not do that, but it's fine. Okay, so what are the 2 types of cases? Now let me draw the hyperplane that our algorithm will return. Okay, so our algorithm will return this brown plane, right? And this needn't be exactly this H. It may be either a counterclockwise rotation of H, or it may be a clockwise rotation of H. Okay, so this corresponds to the G that we will return. Okay, or the normal to this hyperplane will be our A. It's our A, right? And I claim that if E out has to be more than epsilon, right, then there should be, let me call this size of our capital X to be some n. Okay, this is our 10,000, remember. Okay, so in this case, right, what are the points that are actually misclassified? The points that are misclassified are actually in this region. Do you agree? Because anything that is below here, anything that is here is bad in the real world, and G will also call it bad. Anything that is here is good in the real world, and G will also call it good. The region where G and H disagree is what I have shaded, right? So this is where G will call it actually bad, whereas they were actually true points. So these are what are known as false negatives. Okay, G will call it bad. Our algorithm, our learning algorithm will call it bad when they were truly good points. These are this region corresponds to what are known as false negatives, where no, these are false positives where they are below h, which means in the reality they were good points, but our algorithm classified it as bad. Okay. Now, when can this happen? Right? So, this can only happen if from this entire shaded region, not even a single point appeared in S. Okay. Since it's important, let me repeat. This can happen only if from this entire shaded region, not even a single point appeared in S. Why? Because even if there was a single point from this region in your training set S, then for sure, since this is a good point, your training set also gets the correct label, right? So this should be marked as a good point because it is on the positive side of H. And then since your perceptron or SVM was also a perfect classifier, it didn't make any error, your G wouldn't have been this. Your G would have been below this +1. So this error wouldn't have happened, right? So for your hyperplane G to be here, that means in this entire region, nothing was put in your sample. Okay. So let us say this we will, so now, okay, we will just analyze this case and then come back to S. So the probability that our hypothesis, right, our PLA outputs the hyperplane corresponding to G is how much? This corresponds to, yeah, the probability that no point from the shaded region is chosen, right? Okay. But how many points are there in the shaded region? Right? Because we are assuming that your E out of G is more than epsilon, right? So that means we are under the assumption that G had made at least epsilon n errors, right? So which means this area here has epsilon n points, right? This area, this plus this, right? This together has epsilon n points of X, none of which went into S, right? That is why we have your error at least this epsilon. So this also will have greater than epsilon n points, right? So if no point falls in that, remember we are doing 100 samples, right? So for the first sample, what is the probability that you did not pick it from this shaded region? That is 1 minus epsilon, right? So out of n points, epsilon n points are here. Probability to pick a point in the shaded region is epsilon. Probability that it is not from the shaded region is 1 minus epsilon. Now remember our 100 points were picked in an independent fashion, uniformly, the same experiment. So if all the 100 times you missed a point from this region, then the probability is 1 minus epsilon power 100, right? So probability that this G is outputted is something like this, 1 minus epsilon power 100. Okay, but this is not the only way you can produce this error. There is some more detail to it, but I think like it's already a long lecture. Yeah, I mean, I don't want to kind of stop here and then start a new video recording, because I'll again have to, in a normal class I would have done that, but here I think it's kind of, wasting your screen time. Okay, so maybe I'll take 10 more minutes and still finish this. Okay, so here there is a subtle point that I want to tell, and this is going to be extremely important later on. Okay, now if you think about all the possible hyperplanes that our perceptron algorithm can output, there are uncountably many of them, right? There are infinitely many of them. It could be like, any plane. So, but what we have analyzed is the probability of only one particular plane like this, right? So that is not enough for us to give a guarantee that you won't give a bad plane, right? Because there are infinitely many bad planes, so it is not enough to analyze one at a time. Okay. You can surely, using this argument, you can say that, okay, this particular plane has very, very low probability. Like if this epsilon is 0.01, even then, right, this is a very, very small probability. But that's not enough, because you have infinitely many planes, and one of them having very small probability of being outputted really doesn't help. But here, if you now watch carefully, I could have actually said that, I could have changed this event here and said probability, so let me call this angle as theta. Okay, so the probability that PLA outputs a plane or a line, okay, since it is 2D, let me call it a line, which is more than, which is greater than, or which is at an angle greater than or equal to this theta, right? Where this theta, what is this speciality about theta? Theta is where you first cross epsilon and points, right? So what is the definition of theta? Theta is the smallest angle so that the shaded region has greater than epsilon and points, right? So by the shaded region, I mean this. I know I'm not doing a mathematical definition, I'm kind of defining something from the picture, but that is fine. Okay, and the probability that the perceptron algorithm will output a line which is at an angle greater than or equal to theta, since your as you can say that if it has to output any angle which is greater than that, maybe like this, it still has to miss this shaded region. So I'm analyzing only one shaded region, and if in this shaded region you get even 1 point in your testing, in your training data S, you wouldn't have chosen this, 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 and so on. Okay, so that is the idea, right? Since I do not want to clutter. Okay, so this one shot argument, in one shot I am trying to rule out not just one bad answer, but I am going to rule out a large family of answers, right? Any hyperplane which is at an angle more than theta in the positive direction, right? Because in any such plane, I only work with the same shaded region, which has area, which has epsilon and points, and so this is 1 minus epsilon to the power 100. Okay, so in fact this is less than or equal to 1 minus epsilon, because for the other planes it may be larger. Now there is a same scenario, there is a type 2 case where the angle can be in the opposite direction. So if this is some theta 1, this may be some, if this is theta, this may be some theta prime, but everything is the same. Here again, first you can think of one particular theta dash where in this shaded region you have epsilon and or more points, and then you kind of, instead of arguing for one g, you argue for every g that is larger than that. Okay, so now I claim that this event E out of g, E out of g is greater than epsilon only if our perceptron learning algorithm outputs a separating line which is greater than or equal to theta counterclockwise rotated, or greater than or equal to theta prime clockwise rotated from the true, from H. This H is the true hyperplane which separated the real data. Okay, so you have only two kinds of events, right? And hence the probability of this happening, E out of G being greater than epsilon, is the probability of the first thing, which this is what is known as union bound. If something is a union of two events, the probability of that union can be upper bounded by sum of the probabilities, and each probability is upper bounded by 1 minus epsilon to the power 100 plus 1 minus epsilon to the power 100. So this is at most 2 into 1 minus epsilon power 100, right? So this is the guarantee that we can give. Probability that your out of sample error is more, right, is more than epsilon, is at most 2 times 1 minus epsilon to the power size of the net, right? So if your error is what we'll talk about how to bound this and all later. Since it's already too long, let me stop here. But what did we achieve? We showed, in fact, that we have the generalization is possible under this scenario, right? We showed that any plane that the PLA returns, which correctly classifies the given 100 points, has a huge probability of success. Okay, this is a very small number. This is the plane that it returns has a large training error, a large out of sample error with a very small probability. Okay, so that is the idea. Now you can further do your calculus and kind of bound it as 2 to the e raised to minus 100 epsilon, right? And then depending on you want it to be less than delta, right? You want it to be than some delta. So this 100 is actually in your hand. Instead of 100 samples, you can figure out based on epsilon how many delta will you require and so on, right? But okay, those details we will that numerical details we will leave out. But I want you to essentially realize that and the answer to the fourth question is a resounding yes, at least for R2 and separable by line through origin. Okay. Yeah. I know, in the end I had to rush, but we will cover the same things slightly slowly next time. Okay. Thank you.